Hi, this is Mr. Barron, and this is the first lecture dealing with nuclear chemistry. And as you can see from the opening image that we're going to be talking about everything from nuclear power to irradiation used to treat foods, also how a smoke detector works, and how radiation is involved in nuclear medicine. So starting off, this is one of the most important slides to understand where radiation comes from. Believe it or not, it's where's Waldo. So as you start to look for Waldo, and then you start to notice that this person looks like Waldo, this person looks like Waldo, this person looks like Waldo, and the person in the middle is actually Waldo. The thing to remember is this is an analogy, this is not reality for radiation. The analogy is that imagine an element called Waldonium. And if there was this element Waldonium, there would be lots of different atoms of Waldonium out there in the universe. Well, some of them are a little bit funnier than others. Waldo is one of those funny elements, or atoms, of the element Waldonium that actually is a little bit nutty. And you can see he's got his stick, and it looks like he's about ready to injure those two women in front of him. The idea is that there are some atoms that are all part of the same element that are a little bit unstable. A good example of this is carbon. There's actually 3 different flavors of carbon. I like to refer to them as flavors, but we call them isotopes. And isotopes are atoms with different numbers of neutrons, and hence their mass is different. So when you look at the carbon atom on the left, it's carbon-12. That's really close to the average atomic mass. And then we have carbon-13, which has 1 extra neutron beyond carbon-12. That's why it weighs 1 more. And then carbon-14 weighs a little bit more with 1 other neutron, and it has a mass of 14. Once there's this awkward ratio of protons to neutrons, the atom becomes unstable, and that's when it wants to break apart, and that's where we get radioactive particles from. So, what do you think of when you hear the word decay? I'm hoping most of you guys think the word break apart, but if you're thinking right away, you probably are thinking that in the biological sense of the word. But we want to think of decay in the sense of an atom is unstable, then it breaks apart into a particle of radiation and then releases energy as well. That's where radiation comes from. So what does a radioactive atom actually do? Well, we call this nuclear decay or transmutation, and it's the process by which an atom breaks apart because its nucleus is unstable. When we look here at these 2 atoms, we have a parent atom, and it's unstable because it either has too many neutrons or too many protons. It's got an awkward ratio in the nucleus. Notice that the electrons haven't even been drawn. That's why it's called nuclear chemistry. We only study the center of the atom, which is called the nucleus. So it's an atom of plutonium, and then it's unstable, and then it breaks apart, releasing a particle of radiation, which we call alpha radiation. And then notice the parent atom changes into an entirely different atom. It was once plutonium, but now it's uranium. That's why we call it transmutation. It's a change of a parent atom into a different atom entirely after emitting radiation. Later on in this lecture, we're going to learn that we can write nuclear equations that describe this change so we don't have to draw pictures. You'll be learning how to write these by the end of this lecture. Moving on. So there are a couple different particles of radiation. The most common type that people are familiar with is alpha radiation, and what it is it's a helium atom, but without the electrons, and that's why we call it a helium nucleus, because it doesn't have the electrons, and that's why it has a positive 2 charge. So its ejective on an atom is just plain too heavy and it has too many neutrons and protons. It's a positively charged helium nucleus, although very often, as you can see from this picture, we don't draw it with a positive charge. That's because this is nuclear chemistry. We're not even talking about electrons. And also its lowest in energy it actually can be stopped by your skin or a piece of paper. Then there's beta radiation. We have 2 different symbols that you'll see depending on the book that you use. There's this symbol, which is with the E, and then this symbol, which is with beta, standing for beta particle. And you notice that the atomic number is -1, and that's because it's not a proton, it's not a neutron, it's actually an electron that's being ejected. And it's ejected when an atom has too many neutrons, so what actually happens is a neutron is just literally transformed into a proton plus a beta particle. If you remember back to the atomic structure lecture, a neutron is slightly heavier than a proton. So the difference in mass between a neutron and a proton is pretty much a beta particle. It's just an electron. It's higher in energy than the alpha particle, and it can get through your skin. So this image right here is a good illustration of how beta particles are released. Now, there's gamma emission. Gamma emission is emitted along with other particles during nuclear decay. It's high energy electromagnetic radiation. Now this picture below shows the electromagnetic spectrum. Just look at the gray part. That right there is the electromagnetic spectrum. It's energy that's measured in this unit we call wavelengths, which is the distance from one peak to another peak. And there are many different types of electromagnetic radiation, everything from FM radio to television wavelengths to radar, infrared, and then our visible light. You'll see that this colored section has been broken apart. It's actually a narrow band of all the electromagnetic radiation in terms of the spectrum of wavelengths that are possible. And visible light is typically between about 400 and about 800 nanometers. And then, of course, gamma rays. Gamma rays have the shortest wavelength on this chart, and hence they have the highest amount of energy. And that is why they are the most dangerous type of radiation that's released when an atom decays when it's unstable. Then there's positron emission. Positron emission is basically a positively charged electron. It's when a proton changes into a neutron and then you release a positron. Now let's look at the three most common. The three most common we'll be talking about are alpha, beta, and gamma. Alpha radiation is positively charged, so as you see, radiation is being emitted, and then we have two charge plates. We have a positive charge plate on top and a negative charge plate on bottom. Don't forget what you learned in the atomic structure lecture. Opposite charges attract. So alpha particles are drawn towards the negative charge plate, and that's because they're positive. And beta particles are drawn towards the positively charged plate because they are negative. Notice gamma radiation is not affected by charge at all, and that's because it has no charge. It's pure electromagnetic radiation. It's just energy traveling through space. It's not made of any particles like an electron, a proton, or a neutron. Now, this is a quick little chart illustrating the difference in penetrating ability. Obviously, gamma radiation can penetrate a lot further. It's higher energy. And then beta, a little less. And then alpha can't even make it through paper. A Geiger counter is what we use to measure ionizing radiation. What happens is when radiation hits the detector on a Geiger counter, it causes a gas, argon gas, to be ionized. And those electrons are given off, and then those electrons are detected, and that's how it reads the radiation. So this is where we get to ionizing radiation. Ionizing radiation is the most harmful type because it's radiation that causes atoms to lose electrons to form ions. Duh! This is why it's called ionizing radiation. This is the type of radiation that can be harmful. So if ionizing radiation comes in, hits the atom, and an electron's ejected, that's an example of ionization. So ions, don't forget, are atoms that have lost or gained electrons. Here's positive sodium, or neutral sodium turned into positive sodium, and after having lost an electron. Now, these are just some examples of what's ionizing and what is non-ionizing. So the light that we all see, the visible light, the colors that you're looking at on this PowerPoint, that's actually non-ionizing. But notice the types of radiation that we just previously discussed, alpha, beta, and gamma radiation, are all ionizing. Obviously, all the things on the left, most of them you're familiar with, are harmful. Now, why are atoms radioactive? It's because there's an awkward ratio of protons to neutrons in the nucleus that makes an atom or an isotope unstable. So atoms always will break apart. They'll decay into a lighter, more stable nucleus. The idea is that they don't want to be left feeling uncomfortable. So this is what's called the band of stability. So you'll see on the bottom of the x-axis, it's the number of protons. On the y-axis, we have the number of neutrons. If you fall within this band, you are a stable atom. Notice if you're above it, you release beta particles. If you're below it, you release alpha particles. And at the very bottom, if you're around this ratio, you do electron capture or positron emission. So the band of stability is one of the most important things to recognize, which is that there are only specific ratios of protons to neutrons in the center of an atom that leave an atom stable. So if you're above or below it, if you have too many neutrons or too few neutrons, then you will break apart and decay into a lighter, more stable nucleus. Here's another example of band of stability, and it talks about the two types of radiation that are released. Now, what atoms are radioactive? Just as shorthand. Let's first remember that all elements above atomic number 84 are radioactive. Many naturally occurring isotopes of elements below 84 are also radioactive. So the elements that are always radioactive are the ones that have parentheses for their average atomic mass number. Now, if you look at the ones that are not highlighted by these squares, like lithium, lithium can be radioactive. So can carbon. Carbon-14 is radioactive. It's just that you have to have that awkward ratio of protons to neutrons and that causes you to be unstable and then break apart. These atoms are so heavy on the bottom of the periodic table that they always are unstable. Now, let's talk about a decay series. A decay series is a series of nuclear changes that occur until a stable nucleus is reached. So if you begin life as uranium-238, you have an awkward ratio of protons to neutrons. So you break apart either by releasing a beta particle or an alpha particle or doing positron emission, and then uranium changes into thorium-234. Thorium-234 is still unstable, so it breaks apart and keeps breaking apart and keeps breaking apart until it reaches lead-206. So when you release radiation, if you're a radioactive isotope, that's not the end of you being radioactive. You transmutate into other atoms that are also radioactive. The key is that they keep breaking apart until they have the most stable nucleus so that it doesn't break apart anymore. Notice, again, we have neutrons on the y-axis and protons on the x-axis. And uranium-238 is decaying down all the way until it finally reaches the band of stability, which is that appropriate ratio of protons to neutrons. So, let's talk about radiation exposure chart. What are you typically exposed to in your life? What types of sources do you have that give you doses of radiation? Well, 15% of your life is affected by medical radiation, whether it's X-rays or anything else you get. Radon in the ground is another source of radiation. Then there's cosmic, terrestrial, and internal radiation. Internal in you, terrestrial outside of you, and on our planet, and then cosmic outside of our planet, and then consumer products. So radon is actually, since it's the most significant source of radiation for you, radon is actually a daughter product in the uranium-238 decay series that is capable of seeping into the Earth's surface and contaminating living spaces, can ionize lung cells, and possibly cause lung cancer. And you can see that Colorado has a lot of radon. And that's something you've probably heard about being in basements, and that you have to, whenever you buy a new home, you should always check to see if your basement has radon in it, and whether your radon exposure is going to be too high. And that's something to take into consideration because it is a major source of radiation exposure for most people in our country. Now, how much radiation are you exposed to per year? How many years until you start experiencing some effects of radiation exposure? Well, this is a table showing what happens to you with a single dose of radiation. The unit we use for radiation dosage is the rem. Now the rem, notice that it takes quite a bit of rems until you start actually experiencing some effects of radiation. Now let's talk about how we describe radiation with equations. Don't forget this universal symbol we've been using. We use the element symbol, which is X, and if you're dealing with carbon you would write a C there. If it's nitrogen you write an N. Then you have the mass number, which is how heavy that specific atom is in atomic mass units, and then the atomic number, Z, which is the number of protons. So here's an example of that. This should be familiar to everyone viewing this lecture so far, that the mass number is the protons plus the neutrons, and the atomic number is the protons. Alright, there's also another symbol we use, and this is used in nuclear chemistry a lot. It's where you write the whole name of the element, and then you write the mass number. That's another symbol you're going to see. So, let's talk about nuclear equations. Nuclear equations are similar to chemical equations, only it describes changes in the nucleus only, not the rearrangement of atoms. So that's why our unit's called nuclear chemistry and this is called nuclear decay. You can take a look at the two and see that the chemical equation shows hydrogen and oxygen, two different elements being combined. Notice the nuclear equation shows a parent atom, uranium, decaying into thorium and an alpha particle. So, nuclear equations, finding the daughter product. The best way to do this is to make sure that the masses are equal before and after the nuclear change. So the arrow is the division line between before and after the nuclear change. The parent is thorium. The daughter is what we're trying to figure out, which is the atom thorium changes into after it releases this particle of radiation, which is a helium nucleus, which is called alpha radiation. So what you would have to do is go, let's find x. X plus 4 equals 232. So in your head you should be going, 228 plus 4 gives me 232, and that shows that mass is not changing, or at least the mass number is not changing when thorium breaks apart. The atomic number should be the same thing. You should be thinking that 88 is y, because 88 plus 2 is the same as 90. Remember, everything before the arrow has to be the same added up after the arrow. So there's an example of the equation that you would be doing in your head. Moving on. Another way to do this, once you have figured out these two numbers, is to figure out what the element, the daughter, that it becomes. Well, it's 88 here, So 88, you could look on the periodic table and you look up what it is, and only the atomic number, and it tells you the number of protons, can be used to figure out what element it is. Of course, element 88 is radium, so you would write radium right there. So this is what you should be able to do. You should be able to tell me at the end of this lecture, to describe the process of radiation, what this unknown is. If you have any other questions, please shoot me an email or please see me during my office hours.